hydrostatic force on plane surfaces. So this is a submerged plane surface. You can see here, this is a submerged plane surface. So we actually need to analyze the hydrostatic forces which is acting on this surface. So let's say this is a free surface. Okay, this is the free surface, and now we will actually analyze the system. We can say this is the free surface, and all of this, we can say this is the water. We can say the material here, this is actually water. Right, we have a inclined surface. So let's say this is, we can put some name, it is AB. AB, it is a plane, submerged plane, inclined plane, which is submerged into the water. Okay, so this is submerged in a liquid, and this is AB. Now if you look here, it creates an angle. So let's say this angle theta, it creates this angle theta with this free surface. So if we put this dotted line, you see it's create theta degree angle here. If you look this way, that means onto this space in this directions, then you will look, this is actually the submerged plane. So the actual plane is like this, but if you look this way, it looks like this. Okay, so I'm telling again, if you look this way, then you will see it is this, but it is actually this. So now we can say here, we actually, what we are going to do, we need to analyze the forces acting on this surface. So we will calculate the force. So now here, this is the centroid. So this is the centroid C, and this is the CP, center of pressure. Okay, so I'm repeating again, C is the centroid and CP is the center of pressure. Actually, when we have a plane surface, the hydrostatic forces actually form a system of parallel force. So we need to determine the magnitude of the force, okay, and the point of the applications, where it is working. So we will calculate the magnitude of the force and the point of the application, and this point of the application is called the center of pressure, and this is actually the centroid. So now let's say we'll not make this video long, but we'll try to make it short. So here, if we put this dotted line, you see this dotted line, so we can say the location on the distance of the centroid from the free surface is, we can say this is actually Hayes bar. This point, we can say it is Hayes bar or Hayes C. I'm repeating again, you see this is the centroid. So the location, if we put this dotted line here, so let's say we have the point, this is actually, I should write it down this way. Yeah. So the location when the distance of the centroid, okay, we say this is Hayes bar or Hayes C. You can, in different book you can say it is Hayes C, in some book it is Hayes. Or for the center of pressure, when it is the center of pressure, so this location, this we can say it is Hayes star, or we can say Hayes CP, center of pressure. We say this is Hayes bar or Hayes C, is Hayes star or Hayes CP. And this distance you can say Hayes, or we can say that's just the Hayes, this distance. So this is actually the location of this one. Look here, this is the location of CP from the free surface, and we said it is Hayes bar or Hayes CP. Now if we draw a perpendicular line OO dash, this is actually perpendicular to this the free surface, so it makes a 90-degree angle here with the free surface. So the distance from this distance, we can say this is actually y, so distance from here to here, we can say it is ycp. Okay, so distance from this is the strip we have, so distance from here to here, we can say this is actually y, and from the centroid we can say this is yc. So you see I'm using similar one. For the centroid I'm using yc. For this distance we previously used, this is Hayes, so from here to here we said only y. And for the center of pressure we said this is Hayes cp, here we said it is ycp. So that's the distance. Okay, here the area is a, this whole area is a. We can say the length of this small strip, you can say this is b, and this distance, let's say just this, it is dy, very small section. Okay, we took a very small section. Initially we will calculate the forces here. So let's say this is a elementary section, very small section. So for this small section the force is acting, let's say this way, and this force we'll say this is dF, very small amount of force is acting through this dF. Okay, so when we are talking about this strip, the pressure, you can see here this the location of the distance of this strip, it is actually, we said Hayes. So we can write the pressure on this strip, it will be rho g Hayes. We know this formula from earlier, so we can say the pressure on the strip, it is rho g Hayes. Okay, now if we actually want to calculate the pressure force, okay, the force due to the pressure force, this is very elementary section. So we say the force, it will be dF here, dF. So we can say this dF, it will be the force equal pressure into area. So the pressure here, it is rho g Hayes, so say rho g Hayes. And what is area? For this section, area is this is a kind of rectangle here, so this distance and this distance, if we multiply this b and dy, so b and dy, then it is actually the area. Okay, this is the area, and as it is a very small section, elementary section, so we can say this is actually dA. So we can say this is rho g Hayes and dA. This is very elementary section. So dF, this is the whole, the pressure force on this strip, very elementary section. But now if we want to get for the whole domain, then if we integrate it, then we will get it for the resultant force, the force magnitude. So now we will just integrate it. So if we integrate it, then it will be f. So integration of df, that means this integration and this differentiation will cancel out, so we'll get f. Okay, and it will be equal the integration of rho g Hayes dA. Rho density, gravity, g gravity, this is constant, so put it in outside, so this is Hayes dA. So dA, if we integrate it, it will be just a, and for Hayes, now when you are considering for this whole domain, so it will be Hayes bar. So let's say it is rho g Hayes bar a. This is the force. Okay, so this is the force. We will actually use this formula again and again when we will solve some problem. In some books, you will see, I just try to make it simple. In some books, this resultant force, you will see it's given. Okay, it will always act through the center of pressure. So in some books you will see it's given this resultant force, F, it is equal PCA. Yeah, so P is the pressure, rho g Hayes, and this is the pressure and this area, so that's the same thing. So we'll write down, okay, the force, it is equal rho g Hayes bar and A. So this is how we will calculate the resultant force. So now we will calculate this distance, okay, the location, that means we will calculate this Hayes bar. Okay, so to get the haze bar, initially we'll calculate the moment. So if you see on this strip, actually this is the df, the differential force acting, and if we actually want to calculate the moment is the distance, and the force acting this way, and the distance on this surface, this perpendicular surface OO dash. So moment of OO dash, it will be this force into the distance here. So this force is acting, you see, df, and this distance is y on this surface, it is the distance y. So the moment, it will be this force and this distance y. It's not yc or ycp, it's the y. So I can just write it down here. Let's say the moment of df about o dash. This is the force and the perpendicular distance. Okay, this is the force and this is the distance. Okay, so now df into y. Now actually, if we this is for this strip. Now if we want to get the entire body, so for the entire body we need to actually, for the entire surface, let's say for the entire surface, what do we need to do? We need to do the integrations. So for the entire surface, we can say the force is acting F, okay, and this distance is actually, we can say here we can say is ycp or y star, whatever it is. The force is acting this way, so we can say the force F and the distance ycp. Okay, we'll explain it later on. So we can say it is F into y star or ycp, whatever you want. So it will be like df into y. We'll just integrate this. If we integrate this, then we'll get the force. So now df, actually df equal, we know from previous slide, rho g haze dA into y, right? We know it, and now we actually need, yeah, we know rho g haze dA, into y. Okay, so now we actually need to know the haze. So how we can get the haze? So this is interesting. We can go back to the previous slide. If we see this, we are looking for this haze star or haze CP. So this is actually the line this way, and this is the distance. If we consider this is a triangle, look here, this is haze bar, this is this incline, the inclined plate, and it makes an angle theta. So we can we do it like this? Let's say this is haze bar, this is, and it makes an angle. So I will write it down. This is haze star, and for this haze star, what is this distance? It is, we'll say y star. Say this is haze star, and it is actually up to this point. This is the location. So for better understanding, we put the line here and we write it down this way. So up to actually this distance, we write it here, haze star, and then from here to here it is y star. So we can write it as y star, and it makes angle theta here. This is theta. Now for haze bar, you see it's the same thing. This is haze bar, and this is yc, or we can say it is y bar. So as this triangle is little bit smaller, you see this triangle is larger, this is little bit smaller, this is more smaller. So for better understanding, I will write it down. I will draw another one here. Yeah, so it will be now haze bar, and this distance is y bar, and for this haze and y, I will write another one. I will use different color. Let's say this is a smaller one. This is haze, this is y. All created an angle theta. So from the formula, sine theta, sine equal the perpendicular over the projections. So this h bar over y bar, it is equal sine theta. We can just write it down, guys. Here it's like, let's say I can write it down here. This h star over y star, or this h bar y bar, or h over y, it is equal sine theta. I just write it down this way, then we can use always. So here we need the value of h. So what we can write h? H equal y sine theta. So look here, h over y equals sine theta. So we can say h equal y sine theta. So just substitute the value here. Rho g y sine theta dA into y. So it will be rho g is constant, put it outside, so it is y square sine theta dA. This y square sine theta, integration of y square sine theta, this is actually the moment of inertia about O, about the line, that O dash. So we can say it is rho g I naught dA. Okay, it is F into y. This is equal, we got rho g I naught dA. This is actually the moment of inertia. This is the second moment of inertia about that line O dash. Now we have got the F. We are actually looking for this h dash. Okay, we are looking for this. So now so far we have got h f y dash equal rho g I naught dA. Right, so now what we'll do, we will write it down. Then this y star, it will be just rho g I naught dA over f, right? But f equal, we previously calculated f equal rho g a h bar. So now just substitute, just write it down here. So y star, it is equal rho g I naught dA over f equal, we know, rho g a h bar. Initially we calculated this value, we know f equal rho g a h bar. That was the first part. So now you can just eliminate this rho g. So y star, it will be I naught, that inertia, dA over a h bar. Right, we got this. So we know, guys, from this is a y star, so we can use this formula here. So h star over y star equals sine theta. So this equal this equal this equal this. So we can say h star y star equals sine theta. So that means this y star, it will be h star over sine theta. So from here, this is very simple. So we can write it down like this. This y star equal h star sine theta, and it is I naught dA a h bar. Okay, so okay, just 1 second. It will be we actually we did little mistake. Y squared dA is the second moment of inertia. It will be here, you see, y squared dA is the second moment here. It will be sine theta. So that means it is rho g I naught sine theta. Okay, it will be just sine theta. Yeah, so instead of dA, it will be I naught sine theta. Yeah, sorry for that, actually I realized it a bit later. So it will be sine theta. Okay, so that means the h star, it will be I naught sine square theta over a h bar. Okay, a h bar. So I naught sine square theta a and a h bar. Now what is the I naught? Okay, we know I naught is the second moment of inertia. We calculated the we put it is I naught equal integration of y squared dx. So we actually know we can again actually if we go here in the first slide here, we can calculate the I naught for the when we're just calculating for the entire domain. So it will be the IC plus the area A into the y bar square. So when this is the centroid, so we'll discuss this theories later. So this is I naught, we can write it as IC plus the area into y bar square. So I will write it down here. I naught, we know this is equal IC, the centroid, and the area y bar square. So now we previously we know Hayes star, it is equal I naught sine square theta over a Hayes bar. So substitute this value I naught here. So it is IC a y bar square, okay, into sine square theta and a Hayes bar, okay. So if we write down it, so it will be Hayes star equal IC sine square theta plus a y bar square sine square theta, and a Hayes bar, it will be for both section. So now what we can do, we can just cancel out a from here, okay. So you just see what we got here. This is IC sine square theta, this is a Hayes bar, and this is actually, you can see y bar square sine square theta and Hayes bar. So from that relations what we used earlier, we can just write it down, this y bar square and the sine square theta, this is equal, we can write it like this, IC sine square theta a Hayes bar. You can remember this triangular I draw it is in just earlier we discussed. So we can say this is actually Hayes bar square and this is Hayes bar. So we can cancel out this Hayes and this Hayes bar, so it will be just one Hayes bar. So that means the final term we got, it is IC sine square theta a Hayes bar plus Hayes bar. So Hayes bar, it is actually the same thing like the YC. Anyway, so you see here guys, this is the final term we got, the distance Hayes bar, it is equal IC sine square theta a Hayes bar plus Hayes bar. This is actually, we use the triangular formula, that ratio we did for previous one. So this is actually the Hayes bar, the value. So we are going to use this value when we will solve the problem and when we will calculating this Hayes bar. And previously we actually calculated the force rho g Hayes bar A. So the resultant, the force or the magnitude of the force is this, and the value of Hayes bar or the Hayes CP, then we will calculate by using that formula. So you just go through this, you do not need to do these calculations in the exam, but what you need to know is, you need to know this expression to solve this. If you don't know anything from here,